Hello and welcome to this session on organic reaction mechanisms. I am Maria and I am an attainment tutor in our Faculty of Life Sciences. Step Up to ChemHE is a faculty-wide initiative to assist students in developing key chemistry knowledge that can be applied throughout your life sciences degree. So if you have not done A-levels in chemistry, or perhaps you have done A-levels in chemistry, but you feel like your chemistry knowledge might not be sufficient, these videos are designed to help you with some common topics in chemistry. Today we'll look into organic reaction mechanisms. Reaction mechanisms are used in organic chemistry to show how reactions proceed. They describe the breaking and forming of covalent bonds. Many students find them confusing at first. Some try to learn them off by heart without fully appreciating what the mechanism shows, and this is wrong. In fact, reaction mechanisms help us understand what is going on with the molecules in terms of reactivity, so we do not have to learn reactions by heart. First, let's look into some terminology that we use when talking about reaction mechanisms. Starting with what is an electrophile. An electrophile is an electron lover. It is short of electrons, and for this reason, it is attracted to groups which can donate electron pairs. On the other hand, a nucleophile is a nucleus lover. It is electron rich, and it's attracted to groups which can accept electron pairs. A free radical is an atom or a group of atoms with an unpaired electron, and this makes them highly reactive. The key to understanding mechanisms is to master the use of curly arrows. Curly arrows are used to show how the mechanism proceeds. Simply, they represent the movement of electrons in the breaking or forming of a covalent bond. So let's look at this in more detail. When it comes to drawing arrows in reaction mechanisms, you will come across these two types of arrows. The first one, which is with a full arrowhead, shows the movement of a pair of electrons. And the second one, a curly half arrow, also called a fishhook, is a half-headed arrow and it indicates the movement of a single electron. Let's now look at how to use curly arrows. As we said, curly arrows indicate the movement of electrons. They're used as a notation for indicating bonds being broken, moved, or made. Now imagine a hypothetical compound, AB. The bond consists of two electrons, one originally from A and the other one from B. There are two ways in which this bond can be broken. The first one is hemolysis. The electrons in the bond return to be the property of atoms A and B. Note that half-headed arrows have been used, each of these indicating the movement of a single electron, as I mentioned earlier. Movement of single electrons occurs in radical reactions, and these are particularly important for the oxidation reactions of drug metabolism. Then the other way we can break the bond is heterolysis. Here, both electrons have moved to become the exclusive property of A. Overall, A has gained one electron, so now has a negative charge, and B has lost one electron, so is now positively charged. A full arrowhead has been used, showing the movement of a pair of electrons. The third option that we have here is bond forming. The negative charge on A, which is electron rich, is attacking the electron deficient B. The result is a new bond. It's important to remember that the arrow always starts at a region of relatively high electron density and finishes at a region of low electron density or an atom with strong affinity for electrons. Key organic reactions include substitution, addition, and elimination. So let's start with substitution reactions, which are actually relevant in physiological and metabolic processes, in the action of some drugs, and in the chemical synthesis of many drugs. Now we will look at an example of a nucleophilic substitution reaction. Consider bromoethane. With respect to electronegativity, which is the ability of an atom to pull the electron density towards itself. Halogens are more electronegative than carbons, and here is a scale showing some common elements and how electronegative they are with respect to each other. As we see, bromine is more electronegative than carbon. So in bromoethane, the carbon atom has a partial positive charge, while the halogen, in this case bromine, has a partial negative charge. This makes this carbon from bromoethane the electrophile in our reaction, meaning that it will want to accept electrons. Then let's see what happens when we have a hydroxide ion, which is actually a nucleophile, as it is negatively charged, so it will want to donate electrons. The hydroxide ion will attack this slightly positive carbon atom, causing the electron pair of the carbon-bromine polar bond to move onto the bromine, resulting in breaking the bond between the carbon and bromine, and therefore making bromine the leaving group in this reaction. This is the reaction mechanism of bromoethane in alkaline solution to produce ethanol. Overall, we have added an OH and expelled a bromine atom. This is why it is called a nucleophilic substitution reaction. The next type of reaction we will look at is addition reaction, and we will see an example with a compound which contains a carbonyl group, acetaldehyde. So let's look at the carbonyl functionality, which is the carbon double bond oxygen. This double bond is again polarized, as we have seen with the example of bromoethane on the previous slide, because we have two elements with different electronegativities. Again, if we look at the scale, we will see that oxygen is much more electronegative than carbon. So this will give carbon a slightly positive charge, denoted by the delta plus sign, and oxygen a slightly negative charge, denoted by delta minus sign. So let's look at a reaction between acetaldehyde and hydrogen cyanide, which in aqueous solution dissociates to form cyanide ions. And I have shown the cyanide ion only. So this cyanide ion is negatively charged and will attack the positively charged carbon in acetaldehyde. Then the electrons move from the double bond onto the oxygen atom and leave it with a negative charge. Then this intermediate ion reacts with water by picking up a proton to form the product as shown at the end. In terms of elimination reactions, let's look at the dehydration, which means removal of water from ethanol in acidic solution to produce ethene. The lone pair of electrons on oxygen atom move to form a coordinate covalent bond with an H+ ion, where both electrons in the bond are provided by the oxygen. This imparts a positive charge on the oxygen, causing an electron pair to move from the carbon-oxygen bond to reinstate the lone pair of electrons on oxygen, resulting in the loss of a water molecule from the ethanol molecule, but also forming an electrophilic center on the carbon atom. This is unstable intermediate, so the molecule rearranges further, with an electron pair moving from a carbon-hydrogen bond of the methyl group to the positively charged carbon, therefore satisfying the tetravalency of carbon and resulting in the elimination of a proton and formation of ethene. There is some practice here for you to do, two reactions to consider, and identify several things as listed on the slide: the nucleophile, the electrophile, the leaving group if there is one, the type of reaction, the products, and also try to draw the mechanisms. This is also the end of the video, so thank you for watching.